So let's get started on solving first order systems. We're going to focus on the linear ones first. I'll call those FOLSDEs. So what is a FOLSDE? A FOLSDE looks like this. You have n variables, call them x1 through xn, that we're trying to solve for. Each one of those, the derivative can be expressed as a linear combination of x1 through xn. The coefficients of that linear combination are allowed to depend on t, so they could be functions. And then you're going to be able to add a b1, b2, etc. up to bn. Let's get some terminology here. We say that this system has order 1 because there's only one derivative involved in each equation, and we say that it has dimension n or size n because there are n equations and n unknowns. The b1 through bn are the non-homogeneous terms, and if b1 through bn are all 0, we call the equation homogeneous. What's a solution of such an equation? That just means you find functions x1 through xn that satisfy. Okay, so that's what a general FOLSDE looks like. When we talked about a single differential equation, we saw that the constant coefficient case was really useful for helping us get started. Let's do the same thing here. Here, constant coefficients mean all of these aij's are constant. Here's an example. It's a system of dimension 2. There are two unknowns and two equations. So what we're going to do is just convert each one of these into a polynomial equation. And we're going to make sure that all of the variables appear on one side and anything that doesn't interact with the variable appears on the other. In this case, the system is homogeneous, so that right-hand side is 0. We'll do the same thing with the second equation. And now the trick is you just treat this like a system of equations, right? We've got x1 and x2. So how do you solve a system of two equations? You do things like add and subtract equations. You multiply some equation by a constant in order to be able to add and subtract and kill variables, things like that. So let's do that here. What I want to do is hit both sides of the first equation with d minus 3. And I'm going to leave that second equation alone, and now you see that we're in precisely the right situation in which we would want to add the two equations. Now we have an equation in x1. It happens to be a second order equation. Sort of what we're doing here when we solve this particular kind of differential equation with constant coefficients is reversing the process, right? So we went from two equations that were first order and we combined them together to get one equation that was second order. But we can solve this, that's the advantage. Okay, so we solve it just by factoring, and we find out that x1 is something times e to the 4t plus something times e to the t. Okay, that's x1. How do we find x2? Well, just as in solving algebraic equations, once you have one variable, you just plug that formula in to one of the other equations. In this case, I'm going to plug it in to the first equation, and out of that will come, if we add x2 to both sides, a nice formula for x2. Let's work out what that is. So we just apply the differential operator d minus 2 to x1, and we get x2. Now we have both solutions, x1 and x2. I'm going to write them next to each other so that we can get an idea of what that looks like. Notice that there are two parameters here. There's C1 and C2. That tells us that the solution space here is two-dimensional. Where does that number 2 come from? Why would we expect it to be two-dimensional? Because we had two equations and one derivative each. Now, I want to make an observation here, which is that the technique we used was the same technique we would have used for a system of linear equations before we knew any linear algebra, right? We might have learned that in 8th grade or 9th grade or something. So the thing that we picked up on in the beginning of the course when it comes to solving equations is the idea of writing everything down in terms of matrices and vectors. Let's see what happens when we try to do that here. And the idea is just this. Turn my unknowns into a vector. And I will call that x. And it's helpful to remember that because x1 and x2 are functions of t, this vector x should also be a function of t. And let's call this matrix 2, 1, 2, 3. How did we get that? Just by looking at the coefficients. And then you see we can rewrite our system of differential equations in the form that dx dt should be that matrix times x. It's a lot more compact, and it will actually turn out to help us understand how things work quite a bit better. So that's the example in this case. In general, when you have a system of any dimension, you set x to be x1 through xn, The vector B is B1 through Bn, and the matrix A is just given by taking those coefficients and putting them all together. In general, these entries of the matrix A could depend on t. Right now, we've been considering constant coefficients. That means this matrix is a constant matrix, but you could imagine that it varies in time. Now, let's look and see how we reported our answer to this particular system. If we just throw that solution into a vector, we get that. But let's clean that up a tad. Those parameters, C1 and C2, can be brought outside as long as we're willing to write this as a sum of two different vectors. Here again, we can see that, as was the case when we solved single equations, we get a linear combination of two linearly independent solutions. That's not the only thing that carries over. The first theorem that we knew was true of differential equations of any order was that if you told me enough initial information, then there was a unique solution to that corresponding initial value problem. And here the statement is the same. Because these are first order, enough information just means you tell me just the value of x at a single input value. Of course, remember, x naught is a vector, so it's got a lot of information in it. Secondly, the solution set to the homogeneous problem will indeed be a vector space. The dimension of that vector space is the same as the dimension of the initial problem. So if x is an n vector, then you're going to get n linearly independent solutions. Once you have those linearly independent solutions to a homogeneous problem, then you can solve the non-homogeneous problem, right? So by picking a particular solution and then taking any linear combination of the basis solutions to the homogeneous problem and adding your particular solution.